spring pendulum. When we use the term spring pendulum, it simply means a spring, one end tight, the other end free, and it should be in a position to oscillate. That means it should be ready to oscillate. That system would be known as a spring pendulum. At the free end, we'll normally attach one mass. A spring is known for its elastic nature. Elastic nature is that whenever you deform the spring, it's going to restore itself if you release it free. It simply means that there is an elastic force that always tends to restore the body to its original shape, volume, whatsoever it is. Here, in the case of spring, we would say that restoring force will have a tendency to restore its length. Suppose the block of mass m has been suspended over here. Obviously, its weight is acting, and because of its weight, some length will undergo the change. Suppose the change in length in normal equilibrium position is x0, then the force that would develop here is Fkx0. You already know in a spring the force is directly proportional to x, and if you use the equation, it's going to be F equal to Kx. This K is known as force constant. Here, F becomes Kx0. This will be acting upward and mg downward. That means in the equilibrium position, you are going to get this relation. And there is equilibrium, it is not going to oscillate by its own. But soon as you disturb it slightly, means you pull it further apart from x0, you change the length further by x, then in that case, the additional force that will be developed here, additional restoring force, it will be responsible for the simple harmonic motion. And you know, in SHM, force is equal to minus omega square x minus omega square. This is going to be force, that is m alpha, and alpha is given by omega square x. This is the relation. So this side you find the force is kx, and the other side it should be m omega square x. This x will be cancelled, and you find finally omega is root k by m. Two things should be very crystal clear in your mind, that the weight is not responsible for the simple harmonic motion taking place over here. When you additionally displace the mass or you just deform the spring apart from the equilibrium position, then in that case the additional restoring force, that's going to be responsible for simple harmonic motion, and on that basis we got the relation omega equal to root k by n. Likewise, if you proceed, you will find using the relation t equal to 2 pi by omega, you'll get the relation t 2 pi root m upon k. Then here the length, original length of a spring is hardly material. Suppose the original length is L, then in that case equilibrium length is going to be L plus x0. That means the mean position is going to be at a distance L plus x0 from the point of suspension. And if you additionally displace by x, then x is going to be the amplitude of this oscillation. Now, once you decide that the weight is not having any role, that means if you place the spring in horizontal position like this, in this case also, if we just displace the mass horizontally, it will start oscillating, and the time period is again going to be t equal to 2 pi root m by k. So we could say that in spring oscillation, horizontal or vertical position is not going to matter. But one thing is very, very important, without which we can't proceed even an inch. And what is that? In a spring pendulum, we have considered that a spring is ideal. Ideal means a spring is not going to have the mass. If we consider the mass of the spring, it becomes real spring. and then in that case the mass will be replaced, the mass that you have placed over here, that will be replaced by this relation m plus ms by 3, where ms is the mass of a spring. So remember, when you are using this relation, in this relation a spring has been considered ideal. That means mass of the spring has no value, that is considered 0. But if you consider the mass of the spring also, then you are going to get the relation 2 pi. In place of simple mass of block, you are going to use m plus ms by